Welcome to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of system design topics. We are breaking down wide column stores, partitioning, and compaction today. This is a concept first introduction to help you build your system design foundations quickly. If you want to see a deep dive on the trade offs or a specific case study, let me know in the comments. You can find corresponding articles at our companion site, which the link will be in the description below. These videos are kept at a high level to provide the big picture. So if you want a detailed breakdown on any of those things that are discussed either in this video or in some other videos, like a Bloom filter or LSM tree, just ask in the comments. Now let's get back to our video. Let's look at why the filing cabinet got too big. Now, in a relational database, empty columns waste space or require nulls. Wide column stores like Cassandra or ScyllaDB treat sparsity as a first class feature. Notice what's happening in this exploded view. Nothing is stored for absent data. Every row is dynamic because all data for a specific row key lives together on disk. Single key loops are blazingly fast. The trade-off, you lose the flexibility of joins. You must design your schema around your queries, not your entities. You model for the read path from day one. How do hundreds of nodes know where data lives without a central coordinator? The answer is the hash ring and consistent hashing. We take a partition key, like the username Jim, and run it through a hash function like mama3. This gives us a position on a 64-bit ring. The data is owned by the first node it hits moving clockwise. This allows any node in the cluster to independently compute exactly where a piece of data lives in milliseconds, removing the need for a bottleneck master node. Early distributed system had a problem, hotspots. If one node was assigned a huge arc on the ring, it would melt down under load. The modern fix is VNodes or virtual nodes. Instead of one position, we assign each physical node 256 small scatter token ranges across the ring. This forces statistical averaging. Load distribution becomes uniform, and if a node fails, its duties are absorbed by many neighbors simultaneously, preventing a cascade of death for a single neighbor. The cluster handles distribution, but you control the partition key. This is number one cause of production outages. If you pick a key with low cardinality, like country code, you only get 200 effective shards regardless of your cluster size. If you pick a monolithic key like raw timestamp, every single write hits exactly one node, the current time node. The goal is a bounded and distributed key, like a composite of sensor ID and year month, which buckets data predictably and enables parallel processing. Why don't we use binary trees for everything? Because of the I/O transformation. Binary tree relies on random I/O, updating data in place, creating a storm of mechanical disk head movements. At scale, this dies. To survive millions of writes per second, wide column stores use LSM tree, which are log structured merge trees. We fundamentally change the physics. We never modify data on disk. We only append. We buffer in memory and flush sequentially, turning chaotic random writes into smooth stream. Let's trace the write path. Memory first, disk later. When a write request hits, it's split. Copy A goes to the write ahead log for crash durability. Copy B lives in an in-memory sorted structure called memtable. Once that memtable hits a size threshold, usually 128 MB, it flushes a perfectly sorted file straight to disk. Because it was already sorted in RAM, there is a zero sorting penalty at the I/O layer. The disk just receives a clean, immutable block. Once the memtable flushes, it becomes SS table, which is a sorted string table. The immutable part is critical. This file will never be modified again. Each SS table contains three layers: data blocks, index blocks for binary search, and a Bloom filter. Bloom filter is probabilistic gatekeeper. It can tell you with 100% certainty if a key is not in this file. allowing the system to skip expensive disk reads for data that doesn't exist in that specific block. While LSM tree makes writes fast, they create a time bomb called amplification. Every flush creates a new file. If Alice's record is updated 10 times, it exists in 10 different files. That's space amplification. To find her latest records, the database might have to check all 10 files. That's read amplification. Furthermore, deletes aren't real. They are just tombstone markers. If left unchecked, these tombstones and duplicates will eventually grind your cluster to a halt. Enter the engine room. Compaction. This is the nighttime janitor of your database. Compaction is a background process that pulls multiple tables together, merging them via K-way merge sort, and throw out obsolete versions or rotten tombstones. It writes a single clean optimized file. This process is what restores read performance and reclaims your expensive disk space. It's the essential tax you pay for having such fast writes. There are two main compaction topologies. Size tiered groups files by size. It is like a waterfall. It's great for absorbing massive write throughput, but read latency suffers because you often have to check overlapping key ranges across tiers. Level compactions is more disciplined. Outside of the top level, it ensures no two files have overlap ranges. This gives you a predictable, fast reads, but at the cost of much higher write punishment during the merge process. As an architect, use this compaction matrix. There is no perfect strategy. If you are building an IoT ingestion pipeline where writes fly, use size tier. If you are building a user-facing API with strict read latency SLAs, take the write penalty and use level. If your data is strictly append-only time series, time window compaction is practically magic. It groups data by time and virtually eliminates read amplification for time-bounded queries. The read path is a multi-layer pipeline. When a query hits, the system checks the partitioner to find the right nodes, then checks the mem table in memory. If not found, it first runs the neon red gates, the bloom filters. It only proceeds to the index and disk block if the bloom filter gives a maybe. Compaction entire job is to keep this pipeline short by reducing the number of gates the system has to evaluate on the fly. Let's look closer at the gatekeeper. Bloom filter logic is pure math. When you add a key, it flips several bits in a bit array. When you check for a key, if any of those bits are 0, it's a true negative. The key is definitely not there. If all are 1, it's a maybe, a false positive. Pushing your false positive rate from 1% down to 0.1% saves disk reads but doubles the memory footprint of the filter. Like everything in a system design, it's a negotiated trade-off. We wrap up with a fundamental trade-off. Triangle, read, write, and space amplification. You cannot eliminate all three. You can only choose which one to suffer based on your workload. White column stores aren't magic. They are systems whose imperfections land exactly where you can afford them. Well, now for the community. Have you ever been bitten by the tombstone performance collapse or a hot partition in production? Share your stories on the comments. If this episode helped you, please like, share, and subscribe to CSAI Think Tinker Learn. And press that notification icon or notification bell so that you can get notification next time we submit any article on this channel. Visit our site for full deep dives. See you in the next one. Thank you.